Hey everyone, welcome to Anubhav in Tech. You must have already designed Twitter, Uber, YouTube, Gmail, Dropbox, and many such systems in your system design interview or your HLD rounds. But today we are going to design something you use every single day, possibly multiple times a day, without even knowing about it or thinking about it. That little gray text that appears in the Gmail when you're typing an email. Let's say you're typing, I hope you get an auto suggested are well, and you press tab and you see it, right? Or if you write, I hope you are well, or any sentence, you see the auto suggestions kicks in. That's the Gmail Smart Compose feature. Compose simply means writing or creating, right? So whenever you're writing something, this Gmail Smart Compose feature kicks in and assists you while writing or composing a new email. And you have been seeing it currently right now in the Gmail UI. Right? I hope you are well. See, let's come back. So that's the Gmail Smart Compose, and behind that tiny suggestion, there's a full machine learning system with a data pipeline, a transformer model, a search algorithm, and a real-time serving architecture, all working together under 100 milliseconds. Otherwise, it's of no use. It should be live, real time. Now, if you have watched traditional system design videos, you already know the framework, right? The framework that we software engineer follows in an interview while designing any system design or during an HLD round, we follow a framework, a delivery framework, which is we first collect the requirement, which is the functional requirement and the non-functional requirement. Then we move to the data models. We identify the entities, we list them. We write the API endpoints that the users or the internal system will be interacting with. We do the high-level design. We do dive deeps into certain components, identify the bottlenecks and fix it, or suggest the possible solutions. But here, for the Gen AI or simply AI system designs, we do something very similar. I mean, the skeleton is same, but the components are different. So think it of like choosing between SQL and NoSQL. Now you'll be choosing between the model architecture. Instead of designing a cache layer, you are designing a training pipeline. Basically same thinking, but new vocabulary. So here, something goes like this. We collect the requirement, we frame the task as a machine learning task, we do the data preparation part, which is nothing but the ETL. If you are a software engineer, you already know what is ETL pipelines. Then we do model development, evaluation, and then system design. I mean, the complete system design, end to end. For the interview purpose, we'll be skipping evaluation because evaluation is mostly mathematics, and it would be difficult to explain and understand within 45 minutes or the duration of the video. Or also at the same time, you can generalize it. So let's say you are typing something, let's say for int I is equal to something. You're just writing the for loop in your IDE. Code is, AI assisted IDE, let's say GitHub Copilot or IntelliJ with some extension, or let's say VS Code with a client extension. Any IDE with AI assisted coding thing. Your IDE will suggest you the rest of the part. That's the Smart Compose. Exactly, the Smart Compose does the same thing for you within the Gmail. Or you will be seeing it at multiple other places. I mean, this is not only subjected to Gmail. You might be seeing it in the Google keyboard or your Apple keyboard, right? While typing many message in WhatsApp or iMessage, in Slack, in LinkedIn when you message someone, right? You must be seeing it in Google search, Amazon product search, YouTube search bar. Multiple places we see this autocomplete feature. So this video will be a part of my new AI system design series where we'll be taking real world AI features and break them down the same way you would have break down any system design problem in an interview. So if you're preparing for ML system design rounds at companies like Google, Meta, or Atlassian, Uber, or you just want to understand how this AI feature works behind the scene, then this series is for you. Let's get into it. Now let's first understand what it is all about. So whenever we see a user it's typing, let's say I'm typing something, I hope you are well. See, this I just typed I hope you, and the other are well, which is in a gray part, is suggested to me. And the hard constraint over it is that it should be under 100 milliseconds, so that it is real time. Otherwise, it will be not intrusive enough, right? So the solution shown soon that appears in the gray part, it should be within the 100 millisecond latency. And the hard part is that the language is very ambiguous because the next predictive token or the word could be anything. I hope to see you. It could be soon, or Saturday, or still. I mean, any dictionary word, right? So how do we decide which word, or how will the system design which word to suggest? Here you're seeing R well. How the system is able to suggest, because this is the core part, the suggestion, the generation of the predictive tokens. So it uses the context, like who is typing, when it is typing, and what is the prior text to it. And the system must resolve the ambiguity using this context and fast within the 100 millisecond constraint. And we discussed, right, the ambiguous language, multi-layer context, huge source space, 170k words per keystroke, and the individual variation. This is nothing but the user's personalization, or it could be biasness, or it could be the way the user the writing style. All this combined, the model should resolve the ambiguity under 100 millisecond to keep it real time, as real as possible. Now, let's move to the second section, which is very important, the requirements part. Requirements are nothing but what the system does. So we'll first focus on the functional requirements. So let's say the user types, the system suggests the next few words in real time. This is the very first functional requirement, right? Real time suggestion as the user types. Then the suggestion that appears should be only suggested when the model is confident. I mean, low score prediction should be avoided. Should be only shown the high confidence scores. For now, for the interview purpose, we'll be only keeping English. No personalization and no bias suggestions. Then let's focus on the non-functional requirement. The non-functional requirement, it is nothing but how well the system does it. The very first important thing is the latency part. It should be within 100 milliseconds. Then let's talk about the scale. If we talk about the real scale of Gmail, 1.8 billion users. And it would be up to 500 emails per day each user. And assume we have an 1 billion email training set data already available for the training purpose. Just like designing Uber, we ask the interviewer that does it need to be real time? I mean, the ride matching, does it need to be real time? And how many users? Like estimating trips per second. This is no different, exactly same. Now let's move to the next part. Also, I forgot that the system should be highly available. It should be integrated, or the service that emails, the smart compose service should be highly available. But it is not a P1 service. It's not a very critical service. It should be highly available. But if it is not available, that doesn't mean that you won't be able to compose an email, right? Or write an email. It's just an add-on feature. Now the next part is we have to frame the problem as an ML task, right? So this is a step that doesn't exist in traditional system design. Like it's asking like what kind of algorithm will solve this problem. In traditional system design, you'd ask, should I use SQL or NoSQL database? Here you ask, should I use RNN or transformers? The analogy for this is very simple. Like choosing between a SQL or NoSQL is like choosing between RNN versus transformer. Or the other thing could be like monolith versus microservices. Then similarly, for GenAI system design would be encoder only versus decoder only. Or let's say another point of decision in traditional system design is choosing REST framework or GraphQL. And for GenAI system design, it could be greedy search versus beam search. So if you know, or if you already know what is RNN and what are transformer, you can skip the explanation part, because I want to throw some light on what is RNN and what are transformer. If you already know, you can just move to the next part. So let's see what is RNN. RNN stands for recurrent neural network. Imagine you're reading a book, a novel, you're reading a sentence in a novel or in a book, word by word. But you can only keep a small sticky note with you to remember what you have read so far. A single stick note. I mean, you can imagine it as a fixed size blob, or let's say 1 GB of RAM, which can store what all you have read so far. So let's say let's say you're reading, I hope you are, right? Whatever you're writing, whatever you're reading, you're writing something on a sticky note, right? And you're updating when you are reading a new word, the next word. So whenever you're reading, let's say you read I, your hidden state, which is nothing but your sticky note where you're mentioning whatever you have read so far, you will be adding to it. Cool. So I'll explain what is RNN. So imagine you're reading a sentence word by word, but you can only keep a small sticky note to remember what you have read so far. So let's say you're reading the cat sat on the and the next thing that could be predicted could be table, right? So let's say you're reading the cat sat on the. You read the, which is you write on the sticky note. You write something on the sticky note. Then you read the cat. You'll update that sticky note that you have read cat. Then you read sat. I mean, you're reading word by word. Then you'll update it again. And by the time you reach the last sentence, let's say table, your sticky note has already been written so many times that you already forgotten. Just imagine someone as a human. I started reading a book which has, let's say, 20 chapters. Now, currently, I'm at chapter 10. As a human, I might have already forgotten what I read in chapter 1 or chapter 2. This is exactly how RNN works. For a very simple analogy could be, imagine RNN as a single-threaded stateful server that processes requests one by one and keeps a small in-memory cache that keeps getting evicted because you have an eviction policy and a fixed size. It can't look back at the old request. Only what survived in the cache he knows. So the technical version could be it processes only one token at a time, left to right. And after each token, it updates the hidden state, which is your sticky note. So if we consider this text, I hope you are, and it predicts the next token could be memory of I is getting added, and the time you reach hope and the time you reach you, it's getting vanishes. And in machine learning, this is called vanishing gradient problem. Information from back far in the sequence fades away during the training part. So the hidden state, which is the sticky note that we have been carrying to memorize whatever we have read so far, carries forward the memory of whatever we have seen so far. But because it keeps overriding the sticky note or the memory where you are storing everything, the distant context gets forgotten. I mean, the old context you're forgetting. But this is not the same with transformer. Transformers are really different. And transformers are something which are in use since starting 2017 when Google published this paper called Attention is All You Need. Let's understand this as well. Now forget that sticky note that we discussed for RNN. Imagine instead you have an entire sentence laid out in front of you on a table, and now you can look at any word at any time while deciding what comes next. So let's say you are again reading the cat sat on the. Okay, then you have to predict the next token. It could be table or chair or ground. It could be anything, right? To predict the next word, you look at all previous words simultaneously. I mean, parallelly. Instead of reading word by word, you picks up all the words at the same time. Like, which of all these words are most relevant to what comes next? If I ask you which of these words are most relevant to what comes next, so the D in the end is very relevant because we are completing a phrase. Because it says D on the table, on the ground, on the chair, on the sofa, on the bed. So D is very relevant because it completes the phrase. Sat is very relevant because it says something was placed somewhere. And it is cat that was placed and it's the subject. And the D in the starting has very less relevancy right now to predict the next keyword. So it will get it will have the less weight. As you can see, the first D has least weight as compared to the other ones. The word in the last, the sentence D in the last has the highest weight, and the sat and the cat has the other weight. So how much each word matters for the next prediction? So this selective focusing is called attention, and this is something how the transformer architecture reflects. We won't be discussing in depth for this architecture, but I can create a separate video if you want. You can comment down if you need to understand blocks by blocks and components by component what all the transformer architecture mean. But for now, let's keep it like a black box. Because as a software engineer, we really don't need to understand the in-depth of transformer architecture, but we must know what transformer is and how it helps us. So this selective focusing is called attention. The model assigns a weight to each previous word. You can see this. Each previous word, this is the previous word weightage, and how much to pay attention to it when predicting the next token. So for an engineer, I would say transformer is like a multi-threaded server with full request history in memory. I mean, he knows what all requests came in previous to the current. Every new request can query the entire history in the parallel and decide which past requests are more relevant. Like no eviction, no sequential bottleneck. The word with highest attention weights influence. I mean, it influences the next prediction. So that's the magic of parallelism. Because here every tokens looked at each other simultaneously. So you can process the entire sequence in one shot on a GPU. I mean, it definitely requires a lot of mathematics, matrix multiplication. That's why we need GPU for this, because it requires massively faster training is required as compared to RNN sequential one by one approach. Perfect. So now if I want to summarize in one line, RNN reads like you scroll through a, let's say, feed of Instagram reels. I mean, you start from one reel and you end up watching 50 reel and you hardly remember what was the first reel you watched or the second reel or the fifth reel. And by the time you end up closing Instagram, you hardly remember what were the first 3 or first 5 reels that you watched. But Transformer reads, I mean, it remembers the whole history of your watch history, and it monitors, and at any glance it can instantly pick up, or it can recommend or suggest you the next reel. Let's move back. So now comes the another very important part of it, which is the data preparation, the ETL pipeline. Extract, transform, and load. It's a very popular term in SWE software engineering, and if you're not aware of it, you should definitely learn what are ETL pipelines. So similarly, similar to what we do on a daily basis, let's say we want to prepare an ETL pipeline for this Gen AI product, which is Smart Compose. It could be like we have raw emails, we clean it up. We have raw email, we clean it up, then we normalize, and then we tokenize, convert to numbers, and then feed to model. It could be exactly similar to, we have raw logs that we keep getting. I mean, definitely in a microservice architecture or any system, we have TBs of logs, right? Streaming logs. Those logs, we filter the noise. I mean, we remove all the unnecessary part of the logs. We normalize into a format which we can store. I mean, we parse that, store in a DB. It could be any blob store, S3, GCS, and then feed to the analytics that can, so that we can get something useful out of it, right? So the cleaning part we remove. I mean, the raw part we know that's email, web text, which is lots of noisy text and some inconsistent data. We clean, we remove all the pi data, all the duplicates, so that we can further normalize it, and we will create a tabular sort of structure. We'll create a columnar data set, and then we'll try to tokenize each of them. So majorly, that's the, what do you say, idea of the data preparation part. So here the tokenization is like parsing. I mean, similarly to what we do serialization. And this is the step that confuses most people. And let's say, imagine you're building a compiler. You must have read the compiler in your BTech or grad time. Before you can process code, you need to break down, or you have to break the code into tokens. I mean, keywords, operators, identifiers, right? So tokenization does the same thing for your natural language. It breaks the sentence, the complete sentence, into different chunks, right? So, but there are different way of tokenizing or splitting this your natural language. There are 3 ways. You can assume it as like choosing a database type: character level, word level, and sub-word level. Character level is like parsing byte by byte. It technically works, but it has meaningless units, right? Because some part of the text are not useful at all, but it will be still considering, and it will end up consuming more tokens, right? And then there's a thing called word level. I mean, you break down stuff into word by word. I mean, go is considered go completely. I mean, let's say I have to go now. So I have to go now. Each word, you're breaking it down. This is also a good way of doing it. I mean, much far better than the character level, but now it ends up creating a huge vocabulary. I mean, around 300k plus tokens you have to handle. And whenever a new word comes in, that will be difficult, because that's not the part of the vocabulary we already know. Then comes the subword level, or you can say breaking down the sentence into meaningful way. So let's say unhappily, unhappy and ly. These two, the both pieces are common, right? And meaningful. And the vocabulary still is manageable as compared to the 300k tokens. We have now around 50k tokens for this. And this is what the chat, and this is what is being used after ChatGPT 4 and the Gemini 2.5 models. And then we give each token ID. Similarly, a very similar way that we assign primary key to each row. I mean, we identify a column, we put that it should be unique, right? So similar way we assign an integer ID to each token. So it could be let's go. So let's has this token. S is assigned 596, Bo assigned this, and this is assigned 0. You can assume it is like simple lookup table. When you enter 10267, you get let. It's like encoding. You're encoding into a number. And then we feed this sequence of integer to model, which is ready for the training. Then now comes the most important part, the model architecture. And here we'll be choosing the decoder only transformer. Think of the model like a microservice that takes a text input and returns the probability of what comes next. So the transform architecture, where we have 3 variations, right? Think of building a pipeline service. Let's say encoder only, which is BERT, read only service. It reads input and classifies and understands it like a search indexer. Then a decoder only, which is our GPT, Gemini, Claude. It's a write service. It generates output tokens. I mean, token by token, it generates like a code generator. Then encoder, decoder. Again, some of the examples like BART T5. These are like transformer service. It reads input in one format and output in another format, like a translation service. So for our smart Gmail smart compose, which is nothing but text completion, we need decoder only. Because it's a generational task. We need to generate tokens. Cool. So similarly to this architecture, the decoder only transformer has 4 components. The first component is text embedding. So in text embedding, we convert the token IDs, which are the integers which we discussed here. These are the integer. I mean, it is nothing but we did this token indexing, right? So why do we do text embedding? I mean, we have our input token. We then convert into a vector of n dimension. So basically, we try to represent each sentence, or let's say even a word, can be represented in a n-dimensional vector space, where these vectors, as you can see, so the similar vector, I mean, semantically similar vectors are closer to each other. And then we can find semantically similar words or sentences. So that is the same strategy we use it here. So we create the text embedding, which is nothing but we convert the token IDs, which are the integers. For example, let's go, we have these 3 integers with array of size 3 into vectors, which is nothing but array of floats. So here we do it so that we bring closer similar words together in a vector space. For example, happy and joyful are similar words, so they would be much closer or would be neighbors in a vector space, n-dimensional vector space. But happy and sad would be far apart, or let's say happy and car or any 2 irrelevant objects would be far apart in the vector dimensional space. So this is like a feature engineering. We are trying to turn the raw data into something meaningful for the model. Then comes the second part, which is the positional encoding. This is very important. So transformer process all the tokens in parallel because that's the superpower. But that means they lose track of the order. For example, dog bites man and man bites dogs. These 2 words have same words. These 2 sentences have same words but different meaning. So what positional encoding helps is, we inject position information to each word. Think of it like adding a sequence number or timestamp to each event in an event tree. So we add 0, 1, 2, like 0, 1, 2. So we add this positional encoding along with the text embedding and we pass it to the model for a better understanding of the model. Now comes the third part, which is the transformer blocks, the stat n times. This thing actually. So this is the core part, to be honest, the multi-head attention and the feed forward mechanism. I won't be going into the detail because it would take another video explaining this. And then, I mean, this is the block where the actual magic happens. So basically the attention mechanism, it lets every token look at every other token. So 733 will look at 10267, 596 will be, I mean, all the tokens are actually linked with each other. And then they decide how relevant each one is. And based on that, the next output of the token is decided. So the feed forward is just a standard neural network layer, which applies independently to each token. I mean, each token is passed on to the feed forward network layer. And then we see the final prediction, the final output token. Then comes the last part, which is prediction ahead. It takes the final embedding, convert into a probability distribution over the vocabulary. I mean, vocabulary is a dictionary, what all words we have in a dictionary. And then we do a probability distribution over entire vocabulary and see which word has the highest probability of being as a next token, right? So let's say, what's the probability that the next word would be you, a dog, or a zebra, or a cat? So this is like a softmax classifier on the top of your model. I mean, an ML engineer would recognize it immediately. And then comes the next predicted token. Now comes the very important state where we actually train the data. So this training part, we have two stages. I mean, analyze it like this. Maybe we can start training a model from scratch, right? When you can train a model from scratch using common crawl, books, web pages. The basic goal is that your model learns natural language, grammar, some facts, and reasoning. Basically, it is able to predict the next token. And then comes the fine-tuning part. But in the modern days, we really don't do pre-training. I mean, the first part, which is the stage one. Instead of pre-training from scratch, which is extremely expensive, believe me, if you just want to have numbers, to train GPT-3, which is the pre-training part, costed around $10 million, which is extremely expensive. So let's say if you want to train your particular set of data, let's say I have 1 billion email dataset with me, which I want to train a particular existing model. Let's say we can use an open source existing model like Llama, Mistral, which has been already pre-trained on general text data. And then we can fine tune it on our own email dataset or any data that you want to train it on. And this saves significant compute while achieving similar or better results sometimes. Okay, let's move forward. Then comes the sampling strategies. And this one is the core algorithm that decides the model output. I mean, after training, the model outputs the probability. I mean, you have the weights, now you do the inferencing and get the next token. But which one to pick? How do you pick the next word? Then there are two search strategies here. The one is the greedy search and the other is beam search. We'll go one by one. So greedy search is very simple. Always picks the highest probability token. Let's say user typed how, right? So the next highest probability of word is R with 56%, and the second is do is 26. So we'll pick the 56% one, which is R. I mean, similarly, we go layer by layer and we just pick the most popular item, or in terms of recommended system, you click the most popular or the most recommended item in the list. But the problem with this is you lose the diversity. So in a realistic situation, when you are typing something in a Gmail or any other application where you are actually trying to converse, you would want the compose system to help you complete the sentence rather than just predicting the next word, which is frustrating. So we do beam search. Let's understand beam search with an example. So beam search is like in a BFS. So we keep track of top K sequence simultaneously. At each step, we expand each sequence and then prune back to the top K. It is more expensive but far better quality. Just like a BFS with a priority queue, you maintain the window of K best path. So let's see how it is done. Let's say we have a width of 3, or let's say we are only worried about the top 3 suggestions at each layer. So let's say user typed how are. So we'll feed this into our model how are. It outputs probabilities for every possible next word, which is you could be 56. I mean, this is in the decreasing order. So how are the most probable word is you, things we. We'll pick the top 3. We'll prune the other. Now we have top 3 beams. We'll expand them, and the next step is to expand and then feed back one each by each into the model and get the next word probability. So the beam 1, we added how are you. I mean, we picked you, we appended you, and then we are again feeding back to the model how are you, and then we are seeing 3 different options. I mean, obviously we will be seeing more options, but we'll be only picking the 3. So for all these 3 words that we picked, we'll be expanding and we'll be seeing such options. And now we have 9 candidates, right? 3 cross 3. And then we'll do a simple maths, which is matrix multiplication, and we'll see which one, which is a dot product or cross product. We see which one has the highest probability, and we'll pick the top 3. After having a 9 sequence, we'll pick 3, and these are the top 3 words that we had. Everything else is dropped. Now this expansion is repeated until we hit the end of sentence, or the max length is. So the final candidate will look like something like this after repeating it once again. So out of this, we'll pick the most probabilistic sentence. So this is the winner sentence, and this is what we'll be suggesting in the UI. Perfect. So let's move forward. We discussed what was sampling strategies and how do we decide which token to pick next. And then comes the evaluation. In the starting of this video, we discussed that we'll skip the evaluation because it's mostly mathematics, but we'll try to cover it quickly. I mean, before we deploy it, evaluation would be mostly like unit test or like integration test. So in ML world, we do offline evaluation using these 3 techniques like perplexity, exact match, and ROGN or BLU method. So perplexity is nothing how surprised is the model by the real text. Lower is the better. It's like measuring predictive error on a test set. You must have heard of this word perplexity because it's a very popular AI tool, and it is named perplexity is a method to evaluate the model's output. I mean, we can compare 2 model output using this technique. And then let's say exact match, and I mean, we ask this question: did the model's top n suggestion or top k suggested word exactly match what user actually typed? Let's say user actually typed what we suggested. Then we are saying, okay, that's a 1 con. And it's like precision in a recommended system. And then comes the online evaluation. We do this on the real-time monitoring. I mean, it's a real-time auditing on the real user. We see the acceptance rate. I mean, how many times our suggestion was accepted? What is the usage rate? What is the average completion time? I mean, did the smart compose feature make user type faster? And what was the system response time? Whether it was less than 100 milliseconds or not. I mean, it's a simple SLA monitoring. Perfect. And then the feedback rate of human evaluation. These all combines help us to design the final architecture of our Gmail or could be any other application smart compose feature. The final architecture looks something like this. So thank you for watching, and if you liked the video and if you want me to go deeper into any of the specific section, you can comment down, and you can subscribe the channel for more such AI system design related videos. I'm planning to cover Google Translate AI feature, I mean the system design of Google Translate, in the next video. Thank you for watching. See you in the next one.